Right, ladies and gentlemen, welcome to this evening entertainment which will culminate in the battle between, on my right, in the black beret, Team Italy, I believe. No, oh, sorry. Team Italy are in the red. Oh, that's a good start. I was sure the black beret had to be the Italian team. The French. And on my right, in the black beret, the rest of the world. And the competition is going to consist of navigating this obstacle course. But before we get that far, I'm going to try and explain a little bit about what these devices are and how you would program them in APL, so you understand what a difficult task it is these people have been up against today. So, Robot Wars. Now, so here is the script of the decoration, the device that they're going to be using today. And the three important components here are, on the left, the Raspberry Pi, which is it's a complete Linux computer where we're running Dyalog APL. There's a little thing called an Arduino in the middle. I don't know if that gives the Italians an advantage, because that's actually an Italian open source hardware device. And on the right, the all-important motor controller, which provides power to the wheels. Now, the Raspberry Pi you've probably all heard of is this fantastically successful British computer, which is a complete Linux computer. The motivation for this project was to make it very, very easy for schools to get hold of a complete software environment where children could learn all types of programming. So although it's a very, very small device and it only costs about 25 euros or dollars, it is a complete system. It's mostly programmed in Python, but this spring we talked to Romilly Cocking, who I'm sure many of you remember. He was involved in a project to build hardware add-ons to the Raspberry Pi, and we met, and the idea was formed that we should put together this robot with some of his help. So this is a post from his blog earlier this year, where he announced to the people reading the website of his company that sold these add-ons that the Raspberry Pi has learnt a new language, Dyalog APL. The motor controller at the other end, a little piece of red plastic. It can control the two motors. The robots have two wheels, one on each side. There is a power level pin, so we can control how fast the wheel goes. And then, curiously, there's one pin to say whether the wheel should turn forwards, and another pin to say whether it should go backwards. So in all, there's 6 output pins to control to get the robots to move. So why do we have the Arduino when we have a Raspberry Pi, which is a full computer? Well, the Raspberry Pi and a high-level language like Python or APL, certainly even Python, cannot generate some of the very high-frequency pulse signals that are needed to control the motors and the sensors. And we found after we started this project, there's actually quite a number of other projects that people have started on where they combine a Raspberry Pi and an Arduino. The Arduino was sort of the predecessor to the Raspberry Pi and was used for a lot of remote control projects and so on. With the advent of the Raspberry Pi, people are doing what we've done, using a high-level language to generate commands to the Arduino that it then executes. So we've written, most of the software that you'll see in action today is written in APL, but there's a little piece of C code running on the Arduino which just receives commands from APL and controls the pins. And finally, there's a little piece of wire that perhaps isn't worth mentioning, but it was very difficult to deal with, and programmers always like to tell you about the thing that was hardest in their project. So this is something that was pioneered by Philips on TVs in the 80s, and it's just, the thing that's good about it is that with just 2 wires running through a collection of devices, you can control them. So the schematic diagram of the whole thing, we have the Raspberry Pi on the left, it's the green thing, the Arduino in the middle, so just 2 wires going over to the Arduino where we send it these commands, And then the Arduino is actually responsible for setting the pin levels and for reading input from the sensors. At the moment, we only have the one infrared sensor in use for this competition, which makes it quite challenging. But we have also in the project, we've been working on servo motors and a sonar, an ultrasonic sensor, and cameras and so on. So for the technically interested, we have 6 different pin types that we can control. They're numbered with these, or they're denoted with these letters. A for analog output, so that's a number between 0 and 255, which is what we're using to set the power level on the motor. Digital output is either on or off. That's what we're using to say whether we're going backwards or forwards. And then there's a servo output, which is something you use to control a motor that needs to point in a particular direction. We're not using that. We don't have any of those mounted here this evening. And then digital inputs, and something called a pulse input, which some devices generate, where they generate a sawtooth pattern, or a pulse width pattern, rather than just a particular level. And the command language that we've implemented in C just has these 4 commands. You can ask the robot to identify which version of the software it's running. You can reset it. You can set up all the pins that you want to control. So say pin number 5 is an analog output, pin number 6 is a digital input, and so on. And then you can write values to the pins. And the different components of software, the APL stuff is in blue, it's cool, and the stuff that was written in C is orange because it made me feel uncomfortable. Though I actually ended up writing most of the stuff on the Arduino. And what these different layers do is, the highest sort of application layer, we have a class with some properties. So if we want to set the speed for the wheels, we say bot.speed gets -1010. That'll set one wheel going backwards and the other wheel going forwards. That then gets translated through through this description of which pins map to what into a numeric sequence that's transmitted to the bot, and the wheels start turning. And there's a bit of C code here. I'm not going to go into that. I thought it might be interesting, but I can see there are members of the audience who are not finding that particularly exciting. So let's move on. The components involved are the Dyalog APL 13.2, which is a full implementation of Dyalog APL running on the Raspberry Pi, and these interface libraries that were in the boxes there. If you're actually interested in getting the software and building your own robot, you can find all of this software available on GitHub. The link is there, and if anybody's interested, this presentation will also be on the conference website, so you can pick up those pieces of software. And finally, the My Server, our web server, which I'll be showing, which is also running on the web, on the robot. And if I get things to work, I'll demonstrate that in a minute. So the low points of this project, I mean, hardware is really, for somebody who's used to working with software, getting involved in hardware, it's really been an enormously frustrating project initially. I've been putting my robot in a suitcase and flying with it every couple of weeks, and pieces would fall off. And wheels would stop turning. Writing that program in Arduino C, well, you probably really don't want to hear about it, but since it was the hardest thing I did, I have to tell you about it. It's the most frustrating thing I have done for 20 years, I think. Because there's actually no debugger available. And when you send these signals on the I2C bus, it's very timing critical, and if the thing doesn't respond, the request always fails. So essentially any attempt to debug it fails. And either it works or it doesn't. So writing is really just 2 pages of C that we've managed to write. Writing that was a nightmare. But you can now, if you want to join us in this project, you can think of that as firmware. It's just a part of the Arduino, and all you have to do is write these simple commands from APL, and you can control the robot. I think the contestants today spent, a couple of hours learning how to program the device, and then they were into writing their code. So here's one low point. You had this today. Yeah, I mean, the hardware it's very, very cheap, right? Because we're using this computer that only costs $25, we've tried to keep the cost of all of the components down. So that was an excerpt of a talk on a website called TED. If you don't know about TED, it's really something that's worth having a look at. There's some fantastic talks there. And of course, what we're trying to do, and this was a goal actually before we saw this presentation, when we don't have a helicopter, we're only driving around on the floor, but we would like to put together something in APL. We think it can show off a lot of nice APL algorithms quite well to put enough sensors on to drive the robot into the floor of a building and do this, create this kind of map in real time. That's the ultimate goal of the project. So the sensors we've been playing with, the infrared detector on the front, which just measures the distance ahead. We've had a sonar that we can turn around and measure using ultrasonic sound reflection, the distances. What we found, unfortunately, here's some data that I collected with the infrared and the sonar at the same time. So the green square, which I hope you can see, is our kitchen, or Gitter's kitchen, I should say. The robot was placed near one end of the kitchen, and then it rotated 360 degrees and measured the distance to the nearest obstacle in all directions. And you can see the infrared sensor has a maximum range of 80 centimeters, so it didn't actually detect anything other than noise. And the sonar, while you can see very roughly the outlines of the room, there's clearly a lot of reflection going on. So signals are being reflected in the corners. There's a dishwasher here and a refrigerator here, and signals are being reflected. So we're some distance away from being able to equal what you saw on that presentation yet. But we're adding a couple of more sensors. We have an accelerometer, which is just a little chip. It's about that big, that allows us to measure how the robot is moving around. And we have a camera. And the camera is actually has been one of the high points so far in this project. So here's some APL code. I won't go into the stuff at the bottom. The APL programmers can speed read ahead. The statement at the top is really just a Unix statement that you need to capture one image using the camera. So you can say, go out, take a picture, rotate it by 90 degrees, make it 60 by 80 pixels wide, don't wait, and create a bitmap file. And then what we found, which this was really very pleasing and something that you can read about on the blog, this was a high point of the project, that the APL code required to take an RGB picture and calculate where the edges are is really just a very, very small amount of code. It's basically a few outer products. It's very similar to the game of life algorithm, if you've seen that. You're shifting the images left, right, up and down, and then you're multiplying them by this matrix, weighting the center with 8 and then subtracting all the edges. And what it turns out is then if you get a high value in the middle, then you have some kind of edge where you are. Because if you have something which is bland, you'll get a value of 0, because the edges will exactly cancel out what's in the middle. So as soon as you get some kind of variation around a point, you start getting high values there. And using that, here's a sequence of photographs that we took on a dining room table. You have pairs of pictures here. So this is a picture, and then here in red you can see we detected the edges using that algorithm. Here's another picture with the red. And we managed to record this death-defying video on the table in the Dyalog house in Bramley, where the robot is completely autonomously driving around on this table, where any mistake would spell instant death. A 3-foot fall. You can see it's moving quite slowly, and that's because we're actually using the My server to control this, and the way we were driving the cycle was simply with a 3-second refresh on the web page. So the browser was simply posting back to the server every 3 seconds to drive the next movement. It could probably go about 3 times as fast if we didn't do that. It takes about a second to capture an image. It didn't fall off the edge. It's not very daring. The algorithm was fairly conservative. Right, thank you. And now for the live demo. Right, so what I've done here is, so I've started a my server on the bot, and I'm running a web page with some JavaScript in it, where we are able to capture the. So I've now directed my cell phone to that web page. Unfortunately, I can't project that, but it's capturing the position of my cell phone. So I can use this to drive the robot through the my server using my cell phone. It's a little bit erratic, but it can go backwards too. It's surprisingly difficult to engineer a good human-machine interface using. I also think the gyroscope on this phone is rubbish. I won't reveal the make. And because it's a complete Unix machine, I have the disk mounted as a remote drive, and I can just sit here on my Windows machine, and I can look at the source code for that. And I'm not going to go through that, but really just to show you that the total amount of source code to write that application is just about a page and a half. So this is actually something that's becoming very easy to do now with the technologies that we have available. Right, and as I said, the components are very cheap. All of the components here are very cheap, and that's fine for certain types of projects. But we were attracted to another project based on very similar hardware, so a Raspberry Pi and an Arduino, running on something called a Brick Pi, and we managed to get by supporting this project on Kickstarter, we got the naming rights to this robotic arm. So this company called Dexter Industries have 4 published projects, and the first one, alphabetically, is the Apple Picker. And there's thanks to Dyalog from Dexter Industries, and it's a thing that looks like this. We have taken delivery of the Brick Pi, which is the Raspberry Pi is the lowest level of that box there. What we didn't realize is we need to fork out $400 to Lego for the rest, the rest of the components. But we think this technology is going to be something that moves, has much more higher quality and moves much more smoothly. So if you want to follow these adventures, I'm blogging about them every time I have a moment. It's about a month and a bit ago now. I have a bad conscience. But every time we add a new sensor, every time we add a little bit of new software, have another success, getting the robot to do something, we'll be writing about it there. There are complete instructions on how to get all of the components and put it together. So, are the contestants ready?
So, right, so today I ran a workshop for programming these robots, and what they didn't know was that they were going to get through this maze that they had never seen. So we ended up with 2 teams, APL Italiana versus the world, and who knows what will happen. If we can get the teams up here, and they'll talk us through how they did what they did, and then we'll watch the action.
Carlo, would you like to go first then?
We decided, since I'm really boring and John is much more interesting, I will speak first and then. Well, okay. Probably you know that Italians have a very good attitude in finding good excuse for their failures. It can be football, wars, or everything else. And so today we found a very good excuse for an imminent failure. But those robots are much more difficult to manage than you can expect to see just speed something. And the one we received had an extra limitation, which was only if you gave both wheels full speed, both wheels were spinning. Everything else produced a single wheel spinning, with the stuff going this way in a nice, amazing, but a completely useless way. So we spent a lot of time when you were already eating trying to go around this problem, and I don't think we succeeded, because going at full speed means that you have no idea at all how long it will run, because if you go for a very small amount of time, 1/10 of a second is the minimum, because if you send two commands with less than this distance, the horrible stuff will ignore the second. So, and if you do that, once it moves that distance, and the other time this one, is even worse when you make it to rotate, which is so, it's something as you command the stuff to turn, and it does that, and came up whatever. We tried to go around this in a very strange way, I think. We tried to go in the direction of the obstacle, and instead of going away, we tried to move it up to the point that we have a minimum distance, so we know we are facing it really, and then try to move again, but it's not working. At the end, at the very end, this guy says to us that our robot was wrong. There was a digital pin connected to something similar. Yeah. And he fixed it. So now he's behaving in completely different ways. So I think it will be amazing. So I hope I was a good Italian in that. And in any case, even other mistakes has been made by my colleagues, not by me.
So is this working? Yeah. This was a really difficult problem, I think. The only control you have over these robots is to turn they have two wheels. You can turn the wheels at various speeds backwards and forwards. And then there's a sensor that if you look at the sensor, it tells you if it can see anything within 80 centimeters. And that's it. So what we did was we divided into two sub-teams. There were four of us. We divided into two sub-teams. The clever guys worked on an algorithm for getting through a maze, which is not an easy problem. And then us kind of lower-level programmers worked on providing little cover functions like go forward a chunk. So we provided 3 or 4 primitive robot functions: go forward a chunk, go backwards a chunk, turn right 90 degrees or turn left 90 degrees. And there was one called stuff, which returned a 1 if it could see stuff, and 0 if it couldn't see stuff. Yeah, so for instance, to turn right 90 degrees, you spin one wheel in one direction and spin the other in. You set the speed of one wheel in one direction and one wheel in the other direction, and then you do a quad DL, a delay for, I don't know, a bit, and then stop. And so we had to calibrate. That was a trick, calibrate. Now, one of the things is these robots, this is the excuse, this is my line in excuses, is that the robots, this calibration behaves very differently on carpets and on this is effectively ice they're running on here. So that's where we are. But the clever guys who did the algorithm, I believe what we wound up with, I've heard people say if you go into the maze in Hampton Court, one way is you just keep your left hand on the hedge, and if you do that, you eventually will at least get out, I think. And I believe this is what we're trying. We're trying to keep our left hand on the hedge. If I'd been on the algorithm team, I think what I would have done was to put the speed on top speed, both wheels, and then at random intervals do a random spin round, and it would just it would either have 50-50 chance of either getting out of one end of the maze or the other. So, and then later on, halfway through, there was some talk about there being penalty points for bumping into the wall. So, but it will be interesting to see what happens. So let's have a go.
Proceed. Right, so if we can get the team captains up here, whoever they may be, and if you want to bring the laptop up here, John.
Participating.
Yeah, the cameras are not that great, unfortunately.
Are they going to set off together or not?
We hope so. But if we can get both laptops up here, then we'll hit the button at the same time. So the one closest at the bottom of the camera is the world, and the one further away is APL Italiana.
On the floor, so that
Sorry?
This is the world. APL Italiana.
Can you say that a bit louder?
Will you say which one? This is the world.
Yeah, that's the world, and that's APL Italiana.
Thank you.
We'll just wait for John to fiddle.
My job is to type go and hit return. So.
Okay.
Don't we need a virtual assistant to hit enter?
Yeah, we need a virtual
Beautiful, yes, and beautiful.
Oh, sorry. Okay. On 3, both hit enters.
That seems
1, 2, 3. You may put it back on the board.
Can we start again?
As you can see, this is not an easy challenge. So, should we give them an easier course and give them another go? Yeah? Right. If we can do code, then
Grab one of the things and block the exit. At least till you get started.
That'll be fine.
Yeah, we good to go again?
Oh, one's going. Go for it. Okay, so well done, APL Italiana. All those excuses about me changing their robot, and they won. So the little secret here is that most of the training courses were about 3 hours long. My training course was supposed to be 3 hours long, but we couldn't pull them away from the screens, so they were still there when everybody else was eating. It paid off, I think. So well done, guys. So let's have all of APL Italiana up here. All of you guys up here that was in the course, come on. That's Morten's bot. You don't want to do that. We'll just wait for the prize to arrive. And as
Do you have any idea when the prize will be here?
John is just run off. So I built the hardware, and Morten has spent 6 months.
Oh, no. Well, elapsed time,
Yeah, 6 months lapse time. I think Giddo will say that he's spent many evenings.
I will have to say that since we were very young, I've never heard Morten swear so much as while he's been fighting. I mean, he thought it was hardware. Now it turns out that it was an analog pin that couldn't be set while something else was set, so it couldn't both go forward and backwards at the same time. I mean, I'm just referring to what I've been heard.
Yes, it's true. The problem that you had was one I discovered that was on one of my slides, but I kind of skipped over. That when you add a servo to the device, one of the pins stops working as an analog pin.
The downside to this is that in the code, the servo is hard-coded at the moment. So what Morten has...
Also, you will have noticed that Morten showed you this map of my kitchen. No, it was not one thing he did by one survey. Like, I was banned from my kitchen for 5 hours.
So Morten's been programming this for around 6 months, and these guys have done a fantastic job in 5 hours, 6 hours. So well done, guys, and have a eye duck for your office. It does. Thank you. Well done, guys.
Does it say anymore? I think that concludes the evening's activities in here, right? Are we, Ray?
Could you give us an approximate cost of all of the hardware that you put together?
Jason can probably do.
Well, we started with around £100 worth of kit, including the Raspberry Pi. We're not much over that. We're probably, well, actually, we've probably doubled that.
Yeah, plus I have a soldering iron that runs on 110 volts, and I have a soldering iron that runs on 220 volts.
And then there's the cost of the blood, sweat, and tears, and...
Probably about $20,000.
No, probably
No,
about
seriously.
probably about £200 in total for the hardware that we have on Morten's robot, which
Yeah.
also has a camera. There's a 3-axis gyro, though we haven't actually started that in APL yet.
No, I mean, the gyro is really going to be, I mean, the big problem in solving this task was actually impossible to solve because without an accelerometer, having no idea. But I don't, oh, this is working. No. It wasn't a moment ago. Without an accelerometer to measure how the robot's actually moving, you have no idea which direction you're going in. So I'm amazed that they managed to get through the maze without it. It's amazing. But for achieving this two-dimensional simultaneous mapping project, we really need to get the accelerometer working so the robot knows where it is as it moves through a room and can use the sensors. Yeah.
I think that's it.
Okay, any other questions? Otherwise, is the bar open? It is. So we'll see you in the bar and tomorrow morning. Thank you very much.